Now, let's try and determine the asymptotic distribution of sigma hat squared. What are the main ingredients to do this? We want to just look at this and think about what is happening as n goes to infinity, right? And we know already one tool of how to calculate the asymptotic distribution of an expression like this, a sample average. That's the central limit theorem. So let's assume I have y1 to yn IID random variables. Okay. Then the central limit theorem tells us that if I calculate the sample average, I subtract off the expectation, so I center this average, and I zoom in by scaling with the square root of n. Then as n goes to infinity in distribution, this will look like a normal distribution with the same variance as the yi's, for example, y1. Note that I could have also normalized this by dividing by the square root of the variance, but for the multidimensional case, it's going to be easier to think about the variance appearing here. Now, I already mentioned it. What is going to happen here? I can for sure apply the central limit theorem to each one of those two expressions to determine a limit distribution. The problem is that this does not tell us what the joint limiting or limit distribution of these two expressions is going to be. And this is important because what we're doing in sigma hat squared is we're combining them via a function to form a new random variable. So we need to know how they behave jointly. For this, we can use the multidimensional central limit theorem. So let's assume I have actually, OK, let's get rid of this. I actually have random vectors, y1, w1, that I observe. I'm only going to give it to you in 2D, but we can think about what happens in higher dimensions later. So the two-dimensional central limit theorem looks like this. Take the vector of the averages, subtract off their respective means, sorry, W1, and rescale by square root n. OK. Then what's going on is that this expression, as n goes to infinity, is actually a normal distribution again, but this time it's a jointly Gaussian distribution or multi-dimensional Gaussian distribution with mean 0, because we centered those, and a covariance matrix. That's what we call it. So there's a whole matrix describing the shape of this Gaussian distribution. So let's think about what should go into the diagonal entries. We should recover the one-dimensional central limit theorem when we do this. So we should, as the distribution projected out to the first coordinate, get exactly the same limiting distribution. So that means here there's just going to be the variance of y1, and here the variance of w1. The interesting thing now happens when we look at the off-diagonal elements. Here we recover the covariance between the random variables. So think about this as a measure of the linear dependence of the two random variables, y and w. That means that as I get to the infinite sample limit here, this distribution exactly picks up the linear dependence between those two variables. OK, so let's start by calculating the limiting distribution of these two entries and their joint limiting distribution. And then after I erase this, we will see how to combine this to actually get a limiting distribution for sigma hat squared, which is going to be the delta method. So, but first, let's just calculate this matrix here. In the case where, so let me write down what we're going to do. Let's set yi to be xi squared in our original setup, and wi to be xi. Then we have, so then what we need to calculate is first the variance of, let's start with wi. So the variance of wi is just the variance of the xi, and we know that this is sigma squared, which is unknown, but that's fine for now. Next, let's calculate the variance of yi. This we can write as the expectation of x1, let's say, squared. This is the variable, and then squared, minus the expectation of xi squared, and then a square on the outside. OK. This is nothing else but the expectation of xi to the fourth power. And I'm just going to cheat and assume that we know what it is. You can think about how to calculate it on your own. You need to calculate a Gaussian integral. But trust me when I tell you that this is just 3 times sigma to the 4, which at least the scaling you can convince yourself about by writing xi as sigma times the standard Gaussian random variable. And that should tell you that if you take the fourth power of this, sigma to the fourth power should come out. So the only thing that remains is really calculating the fourth moment of a standard normal variable, which is 3. And we subtract off the expectation of xi squared, which is sigma squared, So 1 sigma to the 4 goes away, and we end up with 2 sigma to the 4. OK. And it remains to calculate the covariance between y1 and w1. For this, we know that we can write it as the expectation of y1 times w1. And yeah, I kept mixing up i's and 1's because we can take any one of those to plug it in here. I just noticed that's why I corrected it here. OK, so you have this, and you subtract off the corresponding product of the expectations. So that's x1 squared times expectation of x1. OK. This is the expectation of x1 cubed, which is 0 just by symmetry of the Gaussian distribution, because x cubed is a function that is symmetric about the origin. So think about this. More like that. And if you integrate it up with a function that is mirror symmetric about the y-axis, you'll just end up with 0. So this is going to be 0, and we subtract off sigma squared for this expectation, and another 0 because we assume that our random variables are centered. Yeah, that's also what I need here. I need that I talk about centered centered Gaussian random variables. So the covariance is 0 in this case, but it might not always be. So now that we've determined this limiting distribution, In the next step, we're going to try and see how to combine this result to actually get the limiting distribution of sigma hat squared. And what you can do in the meantime is two things. First, you might want to calculate this in the case where actually my xn's are not centered, but have a mean mu here. And next, you can also try and convince yourself that I actually do need a multidimensional central limit theorem. I cannot simply collect what's going on just by looking at these two terms individually without accounting for the joint distribution. And we'll have an example for you below this video.